In a modern cloud environment, resources are highly elastic. Compute cycles automatically scale up and down as tenant loads shift and cost controls engage. But the large language model agents we deploy on these platforms have a glaring exception: the memory plane. This external store of distilled skills, facts, and trajectories remains rigidly static. Current production systems allocate byte budgets for these memories under the assumption that they will only ever grow. They ignore the reality of shared cloud infrastructure. This introduces a critical stress test. We need to measure what happens to an agent's capability when its memory budget is forcefully squeezed by a cloud provider and then later restored to its original size. Treating an LLM's memory as an infinitely expanding drive conflicts directly with the constraints of cloud economics, guaranteeing a systemic failure when resources contract. Watch these memory models during a squeeze and recover cycle. As we drop the byte budget to 25%, capability predictably crashes. But during recovery, when the budget returns to 100%, capability plateaus well below its starting point, leaving a massive gap. This permanent gap is known as memory hysteresis. The data shows that even the most advanced baseline models suffer permanent damage here. Once the squeeze is over, they carry a residual capability deficit of up to 17 percentage points. The store's capability relies on the exact path the budget took, not just the volume of bytes currently available. To understand why this loop exists, we must look at how these systems handle retention. They all rely on binary eviction. They either keep a memory or they drop it. When the cloud budget drops, standard algorithms try to save bytes by finding the least valuable memories and permanently deleting them. The researchers behind a new framework called CrystalMem formalized this flaw in Proposition 3, establishing a strict mathematical lower bound on the residual deficit. The proof relies on a simple truth. LLM workflows and episodic streams rarely repeat themselves. Once a memory is evicted, the probability of the agent naturally observing that exact data again is near zero. This scatter plot shows the predicted deficit for various binary retention models. Notice how every system, from basic LRU to advanced value-based algorithms, hits a hard floor they cannot cross. Advanced selection algorithms can pick better memories to delete, which lowers the deficit slightly. But because they erase the data completely, leaving no foundational residue to rebuild from, they can never eliminate the gap. Optimizing what to delete is a dead end. To close the hysteresis loop, retention must become reversible. This diagram illustrates the architecture of CrystalMem. It replaces binary retention with a multi-tier fidelity ladder consisting of full, compressed, skeletal, and trace states. Under a tightening budget, CrystalMem does not delete entries. Instead, it initiates a water-filling descent, pushing memories downward into lower fidelity representations. During demotion, the system distills the memory into a minimal residue. Crucially, it saves specific semantic invariants, like key spans, entity tuples, and outcome facts, to act as seeds for future reconstruction. The schedule for this descent is governed by a metric called crystallization energy. The energy equation calculates a precise trade-off. It scores the immediate utility lost by compressing the memory today against the exact number of inference tokens required to rebuild it tomorrow. Deletion is relegated to an absolute last resort. The foundational seeds of the agent's knowledge always survive the squeeze. An agent can hold thousands of memories. The algorithm requires an objective method to rank which entries are the cheapest to demote first. This flow represents CrystalMem's online influence estimator. It continuously monitors the retrieval path, attributing value to memories based on actual RAG task outcomes. Entries that repeatedly contribute to successful outcomes accumulate influence. If a memory is stale or merely decorative, its score decays towards zero. But these memories do not exist in isolation. A complex workflow strategy often references multiple underlying facts. CrystalMem maps these connections through dependency coupling. Certain memories act as hubs, anchoring dozens of other entries. In this graph, influence flows across the citation edges, allowing the hub to absorb the value of the network it supports. Because they accumulate network value, foundational hubs sink to the bottom of the demotion list last. This mathematically protects the core competence of the agent. Eventually, the cloud load lightens. The budget returns to 100%, space to buy capability back. This initiates Phase 3, recrystallization. The agent leverages its idle inference compute, exchanging tokens to step memories back up the fidelity ladder. The LLM reads the minimal skeletal or trace residue saved during the squeeze and uses its reasoning capabilities to physically rebuild a full-fidelity draft of the original memory. Generating data this way carries a severe risk. If the LLM hallucinates during a reconstruction, it will permanently corrupt the entire memory store. To prevent corruption, CrystalMem routes every draft through a strict verification gate. The gate checks the newly generated text against the semantic invariants, the specific facts and entities saved during the initial demotion. If the draft fails to strictly entail every single invariant, it is rejected and discarded. This verification protocol guarantees that inference tokens are safely converted into authentic capability, effectively neutralizing the risk of data degradation. We can see the result of this architecture by returning to our initial test graph. The CrystalMem line tracks the exact same downward squeeze as the baselines, but during recovery, it perfectly rejoins its starting point, forming a closed loop. By retaining verified residues and scheduling demotion by energy, the system reduces the residual capability deficit to less than 1 percentage point. This chart translates that closed loop into a direct economic metric, the cost frontier. Operating at only a 50% byte budget, CrystalMem achieves the exact same capability as the strongest baseline competitor running at full provision. Engineers can provision their memory planes at half the nominal cloud budget and lose zero capability. This framework extends beyond cloud simulations directly onto constrained edge hardware. This schematic details a physical test bed using a Jetson 4 hub and independent robotic arms. The hub serves continuous streams to the arms, while administrators deliberately impose sudden drops in their local storage quotas. Under standard binary memory systems, the storage squeeze causes the robotic arm's task success rate to plummet permanently. With CrystalMem, the arms rebuild their fragmented skills and resume successful operations. Restoring a point of capability through recrystallization uses about 1/5 the physical energy it takes for the robot to execute the real-world actions required to learn the task from scratch. In elastic environments, experiential memory fails if treated as a static storage drive. It must operate as a dynamic, reversible exchange, balancing fixed byte storage against fluid inference compute.